we are coming to the end of our short excursion into complex analysis, and then I will come back to it over and over again, but complex variables per se we are more or less going to be done with it today, and then we will come back to it as and when we need it. But there is one more small digression that I would like to make before we move on to the next topic, and that has to do with integral representations for another class of functions, special functions, which you are all familiar with, namely the Legendre functions. Now I already mentioned, and we saw examples of integral representations of the gamma function, the beta function, the Riemann zeta function, and so on, but there are a whole host of functions in mathematical physics used in physical problems, like the Legendre functions, the Hermite functions, the Laguerre polynomials, Chebyshev polynomials, Gegenbauer polynomials, and so on, all of which are related to something called the hypergeometric equation, and these functions have a lot of interesting special properties. They are called special functions for that reason, and they have a huge number of properties which have been studied. Now what I would like to do today is to show you that a couple of these functions, the Legendre functions in particular, have certain very interesting integral representations, and from those representations you can actually define these functions in a much broader range of variables than originally introduced, namely the Legendre polynomials were introduced PL of x for x between -1 to 1 and L an integer 0, 1, 2, 3, etc. But today we would like to generalize this a little bit. I recall to you, so let me call this Legendre functions. Recall that these functions are solutions of a certain specific second order differential equation, which you would normally write down in elementary treatments as equations in a real variable x, say between -1 and 1. But you do not have to do that. The equation itself is valid for all values of the complex variable z, and it reads something like this: 1 minus z squared d2 over dz2 minus 2z d over dz plus, instead of the order L restricted to an integer, let me use another symbol nu, say, which is going to take unrestricted values over the complex domains. So nu times nu plus 1, this thing operator acting on some phi of z equal to 0. This is Legendre's equation. And in general this is some complex variable parameter, and this is also a complex variable. Okay. The solutions of this second order differential equation, there are two linearly independent solutions, and they are the ones which you call the Legendre functions of the first and second kinds, and the first kind is p nu of z, and the second one is denoted as q nu of z. So this is the Legendre function of the first kind of order nu and argument z, and ditto for this is the one of the second kind here. Now this is the function which for integer values of nu like 0, 1, 2, 3, etc., and for z between -1 and 1 you call the Legendre polynomials, but this is a much more general thing than that. And the Legendre polynomials are special cases of this function here. Okay. There are several things you should observe about this equation. The first one being that this is really an eigenvalue equation for the following quantity. So you could also write it as d over dz of 1 minus z squared d over dz phi is equal to nu times minus nu times nu plus 1 phi. So cast in this form it comes under the category of what are called Sturm-Liouville equation, the Sturm-Liouville problem, and then there is a huge literature which tells you how to solve such equations and so on. No doubt you are familiar with the solution to this equation by the method of series, the Frobenius method of series, and then you get for special values of L, integer values of nu, you get the Legendre polynomials as a solution. But what I would like to emphasize is that this thing here, these functions actually are valid, have valid representations for complex values of z. and here is what the representation looks like. I will not derive it, I will just write this down explicitly. Consider the following, consider as a function of the complex variable t, consider t squared minus 1 over twice t minus z to the power nu as a function of nu for some arbitrary complex z, for some given z, and nu some complex number. In general, this function has singularities in t, and where are these singularities? Well, when this is an arbitrary complex number, you have winding points all over the place. You have a winding point at t equal to plus 1, another at t equal to minus 1, and a third one at t equal to z itself. So in the t plane, there is a singularity at plus 1, there is a singularity at minus 1, and these are in general winding points, they are branch points, and there is a singularity at the point z, which could be anywhere. So let us say z is here, this point. So here is a function with 3 branch points, and in general there is also a singularity at infinity, because this thing goes like t to the power nu at infinity, and definitely there is a singularity at infinity. So there are all these branch points in this plane. Okay. Now a contour integral representation, if it is a closed contour, I have already pointed out that when you have branch points, you can have a closed contour provided the contour returns to its original, the integrand returns to its original value once you come to the end of the contour, to the starting point once again. Now when was that going to happen? Well, if I encircle the branch point at t equal to plus 1 once in the positive sense, I pick up a phase e to the 2 pi I nu. If I do it in the negative sense, e to the minus 2 pi I nu. Similarly for the branch point at t equal to minus 1, and if I encircle the branch point at t equal to nu, t equal to z once in the positive sense, I pick up e to the minus 2 pi I nu, because it is in the denominator here. So this immediately suggests that if I go around the singularity at plus 1 once in the positive sense, and at t equal to z once in the positive sense, I am going to come back to the starting point. In other words, I can choose cuts in such a way that encircling both these things and nothing else once in the positive sense brings me back. So this means that there exists, if z is here for example, just for illustration, this contour would be a closed contour, which is equivalent to saying that I can choose the branch cut to go like this, and the cut from here I can choose to go off to infinity in this direction. So with suitable choice of cuts and phases, this is a closed contour, so let us call that C1, and this is, it says you encircle 1 once in the positive sense, z once in the positive sense. Okay. Similarly you could do that with minus 1, so you could also do it minus 1, but there is one more thing you can do, and that is, here is 1, here is minus 1, here is z. You could encircle this once in the positive sense, and this guy here once in the negative sense. So you could do this. This contour, let us call it C2, this is 1 plus minus 1 minus, because the first one picks up e to the plus 2 pi I nu, and the second one picks up e to the minus 2 pi I nu, and they cancel, and you are back to the starting point here. So regardless of how I choose cuts and so on, I can arrange it such that this contour is a closed contour once again, and it is clearly different from the contour C1, very different. Now the cut from z, the branch cut from here goes off to infinity in that direction, we do not care. There is of course a branch cut from here to infinity, another one from here to infinity, etc., but it does not matter. We have ensured that by doing this you are back on the first sheet here, starting from the principal sheet you are back to that original value. The phases have cancelled out. Well, there is one more possibility, and that is in the t plane you have z here. You could have encircled these two both in the positive sense, and this is 1, this is minus 1, and that is z. So the cut is like this, and this cut can be arranged to go off to infinity in that direction. This too will bring you back to the starting point, and this contour is C3. So I want you to convince yourselves by playing around with this that these are really the only independent ones, there are not any more, and moreover that this contour is related, whatever you get here is going to be related to whatever you get here by change of variables t to minus t or something like that. Okay. So really it is just C1 and C2 that we have to deal with as independent contours, and it turns out that this function p nu of z equal to 1 over 2 pi I over the closed contour C1 dt over t minus z times precisely that integrand there, t squared minus 1 over twice t minus z to the power mu. With this extra factor here, this turns out to obey exactly Legendre's equation and reduce to the Legendre polynomials for integer values of nu, as we will see. And q nu similarly turns out to be 1 over, I am not sure about the factor here, but pi times, I know for sure that there is this factor, that is a sine pi nu, and then over C2 dt over t minus z t squared minus 1 twice . So the two solutions of Legendre's equation, the linearly independent solutions, are given by suitable contour integrals of this integrand, of this simple integrand, which has branch points at +1, -1 and the point z. And from this you can read off all the properties. Incidentally, you can verify that these functions satisfy this equation. It is not such a trivial job, but that is definitely doable, as well as all the other properties which we are going to examine now. Okay. So to start with, let us look at what happens when you have non-integer values of nu in general. Then it is clear that you expect the following things to happen. So nu not equal to integer in this case. Well, we will see a little later when we talk about singularities of integrals today itself, that this function p nu will have a singularity when the following happens. How can such a contour integral ever have a singularity? Well, remember that the whole thing is a function of z. So if I move z, this pole moves around, this branch point moves around. One thing that could happen is z tends to 1, of course it collapses, that could happen. The other thing that could happen is that z moves around and hits -1 in the z plane, and when that happens you can't distort this contour away, because this closed contour is trapped between the singularity at -1 and the singularity of the integrand at z itself, and it is pinched between them and you get a singularity. In which variable? In the variable z. Okay. So we expect that this thing here p nu of z is singular at z equal to -1, okay. And indeed that is so. We can show explicitly that there is a singularity, a certain singularity, a branch point in general at the point z equal to -1. Okay. Keep in mind the fact that the contour is in the t plane, but the function whose analytic properties we are discussing is a function of z. So you move z around in the z plane, and this movable singularity in the t plane moves around and it does things to the contour. That is how singularities would arise. What about this guy? What kind of singularities can you expect here? Well, here the only way I can have a singularity is if this branch point here attacks either +1 or -1, and then I can't move the contour away. If it comes towards this point I can distort it a little bit, etc., but if it hits +1, if it is directed towards +1, I am stuck. So I immediately expect that Q nu is singular at z equal to plus or minus 1 at both points, okay, for general values of nu. That is my initial expectation. This is what is going to happen. Okay. Now let us look at what happens when you have integer values, and then a whole lot of cases would arise immediately. So let us look at nu equal to L equal to 0, 1, 2. So let us look at the non-negative integers first and ask what happens to PL. Well, in that case this branch cut disappears completely, right, and then what happens to this? So I set nu equal to L where L is an integer, there is already a t minus z here, okay. And then what happens? There is no branch point at +1 or -1, it is gone, it is to the power L here, some non-negative integer power, and you got a t minus z to the power L here. So there is a pole of order L plus 1 at the point t equal to z. And what does this contour integral reduce to? This integral reduces, here is +1, here is -1, and there are no singularities at these points now, this is gone, and all you have is a pole and the integral encircles it in the positive sense. And you just have to evaluate the residue at this point in order to find out the value of the integral. So it immediately says PL of z, what can it be? Well, it immediately tells you that you have a pole t minus z to the power L plus 1, you need the L plus 1th derivative or Lth derivative of this function to find the residue, okay. And t squared minus 1 to the power L, positive integer L, is some polynomial, and you need the derivative of that at t equal to z. So you end up with a polynomial. So this says is a polynomial and you can even write a formula, it is 1 over 2 to the L, L factorial dn over dn over dt to the power n, t squared minus 1 to the power n at t equal to z. I might as well write this as equal to 1 over 2 to the L, L factorial dn over dz to the power n, z squared minus 1 to the power n. That is what PL of z is. Do you recognize this formula? What is it called? It is the Rodricks formula for this Legendre polynomial, okay. For PL of z. And it is true for complex z, it is true for arbitrary complex z, not just for z equal to x equal lying between -1 and 1. So this function PL of cos theta, which you are used to, cos theta is a number between -1 and 1, it is a real number, real variable, you do not need that, it is true in general. This Rodricks formula is true for complex values of z as well. PL of z for arbitrary complex z is a polynomial of order L. What happens if L is a negative integer, say minus L minus 1, where again L runs 0, 1, 2, 3, etc. What would happen then? So what about P minus L minus 1 of z, where L equal to 0, 1, 2, etc. What would happen then? Well, go back to the general formula and put nu equal to minus L minus 1, and this time you end up with a pole at t equal to 1, because this gets in the denominator with some integer power, and you have a pole at t equal to 1, and there is no singularity at t equal to z, that goes up in the numerator, okay. So once again the contour collapses, but it collapses to this. there is a pole at 1 and there is this, and Z is sitting somewhere here, and here is -1 from this point. Okay. And again you get some derivative or something like that, and I leave you to verify that you end up with P minus L minus 1 of Z equal to PL. So there is a symmetry property of the Legendre polynomial about the point -12 in the order L. You should not be too surprised to see that kind of symmetry, because if you go back to the differential equation, notice that L times L plus 1 appeared, right, and you can write L times L plus 1 as equal to L plus a half whole squared minus 1/4. It is the square of this that appears. So it is clear there is a symmetry about the point -12. So that is why you have that symmetry, you have P minus 1 equal to P0, P minus 2 equal to P1 and so on. In fact it is true in general, because what appears in the differential equation is nu times nu plus 1. So I would expect that symmetry to be valid, and it is indeed true. It is indeed true that this is so. For arbitrary complex nu, this P, the Legendre function of the first kind has this symmetry property. Okay. But we see again that P minus L minus 1 is also a polynomial. Okay. What about Q? So let us look at what Q does, and Q is sitting there, and now we got to ask what does. So we have L equal to 0, 1, 2, etc., and we are looking at QL of Z, and if you look at its integral representation, we had here a nu. This contour now encircles the singularity at 1 in the positive sense and at -1 in the negative sense, and what does it do? Well, this thing becomes an integer, but you still have this sitting here. At t equal to, at nu equal to a positive integer, this contour integral vanishes, because the singularity that it encircles has disappeared. It is t minus 1 to some power, t plus 1 to some power, which are integer powers, so this integral vanishes. On the other hand, this vanishes too in the denominator. So just as in the case of the gamma function, where for positive integer values of n we had an integral that vanished, and we had a denominator function sine pi nu or pi z or something which also vanished, and you had to take a limit. In exactly the same way you have to take a limit here, and the answer is some finite number. We will see what number it is, but let me give the answer here. It turns out this quantity here can be written as 1/2 log x plus I think it is 1 plus x over 1 minus x. I am not sure about the sign of this log, times P L 1 plus z of z plus a polynomial of degree L minus 1 in z. So typically what happens is that you have a logarithmic singularity at +1 and -1, and then you have a polynomial part. But I already argued from the general representation that QL is expected to have a singularity when z hits plus or minus 1, because what happens is that the singularity at t equal to z comes and pinches with either +1 or -1, pinches the contour. So sure enough there are logarithmic singularities. We will see later why it is logarithmic rather than anything else. Okay. In particular, we know that P0 of z is 1, and this disappears, and you have Q0 is just a log. That is another name for this log 1 plus z over 1 minus z. But the other QLs, the higher QLs, would be some logarithmic function multiplied by this polynomial plus some polynomial here. What about negative values? Now we run into a slightly different situation. In the case of negative values, this guy here goes in the denominator and the contour integral does not vanish. So it is some finite number, the contour integral, but this vanishes here. So the result is q nu of z, as nu tends to a negative integer, has a singularity in nu, and it turns out that q nu of z equal to 1 over nu plus L plus 1, this fashion, where L is 0, 1, 2, 3, etc. So, the singularity is at minus 1, minus 2 and so on, multiplied by a residue, and the residue interestingly turns out to be PL of Z itself plus regular part. Okay. So, the Q's and P's are intimately related to each other in this fashion. So, as a function of nu now, there is a singularity of this function here. So, the right way to look at all these functions is as functions of two complex variables, of the order as well as the argument. Most of the time you are interested in the argument, but the order also displays very interesting properties here. Incidentally, the fact that there is a log here that is sitting here suggests that what is really happening is you are integrating PL in some fashion with some kernel which is like t minus z or something like that, and sure enough there is a connection between the two which does the following. Sure enough, QL of z equal to 1/2 minus 1 to 1 dt PL of z over t. This is z minus t. So, for this is valid for L equal to 0, 1, 2, etc. So, you have an expression for QL as an integral over PL multiplied by this Cauchy kernel 1 over t minus z from minus 1 to 1. And this formula is valid only for non-negative integer values of L. For negative integers this is perfectly fine, but this is singular. Okay. So, this thing will tell you that you can expect a logarithmic singularity, because when can you expect a singularity of this integral itself? PL is a nice function, it is just a polynomial, but this integral, the integrand has a pole at t equal to z, and when z hits either minus 1 or plus 1, you can't move the contour away and you expect a singularity, and that is how you end up with this logarithmic singularity, as we will see a little later. Okay. In fact, in general this is what happens to in the z plane to p nu of z. For p nu of z, there is a singularity at minus 1 and there is a cut running all the way to minus infinity. For q nu of z, again in the z plane, singularity at 1, singularity at minus 1, and there are cuts running all the way to minus infinity conventionally. The discontinuity of QL across this cut, or q nu across this cut in general, is proportional to p nu. That is what we will see from this formula. The discontinuity here, so by what do I mean by discontinuity? I am asking what happens if I take, if z approaches the real axis from above and from below, and you ask what is the difference between the two functions. That is the discontinuity. So, discontinuity q nu of x less than minus 1 is proportional to q nu of minus x. I am not going to prove this, but the jump here is proportional to q nu at minus x out here, and the discontinuity between between minus 1 and 1 is proportional to p nu of x. So, discontinuity of q nu of x minus 1 less than x less than 1 is proportional to p nu of x itself. And similarly, the discontinuity here, discontinuity p nu of x x less than minus 1 is proportional to p nu of x. So this shows you can actually write dispersion relations for these functions in terms of these discontinuities here. So the q's and p's not only satisfy the differential equation, but they also satisfy these integral equations of this kind, okay, because of these interesting analytic properties. Let us see where this comes from. I made statements about this logarithmic singularity and so on. Let us see where this comes from. So let us ask for a very elementary treatment of how functions acquire singularities. Functions defined by integrals acquire singularities. So let us start with a simple example. Let us look at an example like f of t equal to integral 0 to 1 dt over t minus e. Let's see. Okay. The simplest possible thing. This is an analytic function of z wherever this integral exists, but you expect it to have some singularity somewhere, right? Now where would you expect that? Well, in the t plane the contour is a line segment running from 0 to 1. That is fixed, it is pegged at the two ends and it is like a rubber band. You can stretch it, you can do all kinds of things, but you cannot take away the endpoints. On the other hand, in the z plane, if z is any value here, there is a pole of this integrand at t equal to z, so it is sitting here, this pole. If I move this z around in this fashion, this pole moves around in the same fashion. But when this comes and hits 0 out there, then this pole attacks that point and you cannot move the contour. On the other hand, if I took a path like this and went down, there is no point problem at all, because this thing would come down like this and I can move the contour away ahead of it without changing the value of the integral, right? Because the function is still analytic. I do not let this singularity hit it, I just distort it as much as I like. This thing is going to fail only on two accounts. One of them would be if the contour gets dragged all the way to infinity, the integral may diverge. And the other is if this singularity hits the origin or the end point of integration, I am in trouble. And these are called endpoint singularities. When a singularity of the integrand attacks one of the endpoints of integration. Pardon me? Pardon me?
What if it is closed around that?
It's not, the contour is not closed. So I am talking about an integral. I am talking about singularity of an integral which is a line integral from one point to another. If it is a closed contour, there is no bound, there is no end point to it. Then what can happen is the pinching that I mentioned earlier, and we will come to that in a minute. So endpoint singularities occur when the integral is defined with two endpoints the usual way. This has endpoint singularities at z equal to plus or at z equal to 0, z equal to 1 at these 2 points. Well, we can corroborate this by just doing the integral. Let's just do the integral and be done with it, right? In this particular case, you can do the integral explicitly. So what does this give you? This is equal to log t minus z running from t equal to 0 to t equal to z. So that is equal to log t minus z or z minus t, sorry, t equal to 1. So that is equal to log 1 minus z over minus z. So that is log z minus 1 over z. And there we are. I know that this is log z minus 1 minus log z. Log z minus 1 has a singularity at z equal to 1, logarithmic branch point, and it has a logarithmic branch point at z equal to 0. But I do not need to do the integral in order to come to this conclusion, because I could have had a more general integral like this multiplied by some phi of t, some nice smooth function such that the integral exists, and you still have endpoint singularities at these 2 points. Okay. Of course, it is not equal to this anymore, but barring accidents generically it is going to have endpoint singularities at these 2 points here. Okay. Now what about this phenomenon of pinching? So let us look at the next example, which is the following: f of t equal to integral say -1 to 1 dt over t squared minus z squared. Let us look at this, integral. Okay. Where would this have singularities? The first thing you have to do when you want to analyze how an integral becomes singular is to ask, where are the singularities of the integrand, and then look at how those singularities move as the variable z moves. Okay. Where are the singularities of this integrand? At t equal to plus z and minus z, and they are both simple poles. They are both simple poles, and the contour runs like this. In the t plane you have 1 here, -1 here, this is your contour, and in the z plane, so there is a singularity at z, so if z is somewhere there is a singularity at that point, and the other singularity is at t equal to minus z, which is at this point. It is immediately clear that if z hits plus or minus 1, minus z hits -1 or +1 the other way, you have endpoint singularities. So I expect that when z hits +1 or -1, you are going to have endpoint singularities. But there is one more possibility. As z moves towards the origin, this point moves here and the other point moves here to this side, sorry, it remains on this side, moves here. What will happen as z hits 0? The contour gets pinched between the two and there is no escape. Okay. Otherwise, if z moved down like this in this fashion, there is no difficulty at all. Z hits this path, so I just distort this in this fashion. Well, this point starts moving up, so I distort the contour here, and then you have this and you have that, and the integral is still well defined. Okay. The only way it will not be well defined is if z heads for 0, and then of course the pole at -0 and +0 coincide, but from opposite sides of the contour they pinch the contour between them, and then you have a singularity of the integral. What would you call such a singularity? Well, the last time it hit an endpoint and you called it an endpoint singularity, and now it is pinching the contour, so you are going to call it a pinch singularity. Yeah, this is a pinch singularity. So it has endpoint at plus or minus 1, pinch at z equal to 0. This is all in z. Okay. What happens if you do the integral explicitly? So let us just do the integral and see what happens. You have f of t equal to integral -1 to 1 dt, and this can be written as 1 over t minus z minus 1 over t plus z, 1 over 2z, right? T plus z minus t plus z. You can write it in this form. So this becomes equal to 1 over 2z log 1 minus z over 1 plus z times is a -1, and there is this minus sign, so it is equal to -1 plus z over 1 plus z with the minus sign. Let us do this slowly. Minus log 1 plus z over 1 minus z. Right, which I can write as plus log and invert this, so I can write it as a factor of 2, and that is it. This is gone. That is it. And where are the singularities of this function? you do end up with an endpoint singularity at z equal to +1, a logarithmic branch point, another one at z equal to -1, logarithmic branch point. These are endpoint singularities. And what about this guy? It is a pole, it is a simple pole at z equal to 0. But where does this pole occur? On all sheets other than the principal sheet of the logarithm, because on the principal sheet of the log 1 is 0. This whole thing goes like z on top, and that cancels this, so the residue gets cancelled out. We already saw an example of this phenomenon. When you have this, when you have these poles multiplying logarithmic functions, you got to be very careful. It could turn out that the pole vanishes in one of the sheets, or exists on all sheets except a few of them or something. In this case, there is a pole at z equal to 0 on all except the principal and that is a pinch singularity at this point. Now the nature of the singularity depends on the nature of this, whether it is a pinch or an endpoint singularity, and on whether the integrand itself has a branch point or a pole. In all these examples we looked at integrals which have got poles, but we could easily consider an example where you have a branch point. Look at a thing like this. So we want to keep this real, so square root of z squared minus t squared. Look at what happens now. Okay. Where does the integrand have singularities? At plus or minus z, but what sort of singularities are those? They are themselves branch points, they are both square root branch points, okay, because it is just 1 over square root z minus t, 1 over square root z plus t, right. So now you have a contour integral which runs from -1 to 1, but you have a branch cut and you have another branch cut like this. Once again, when these fellows come and attack either the endpoint or they pinch the contour at z equal to 0, you are going to expect singularities, but I leave you to verify what sort of singularities those are. They are not going to be the same as in the earlier case when you did not have the square root here, because now you really have branch points attacking these things here, and this could change things completely. Okay. So once again, this integral is doable, it is very easy to do this, you just have to make a substitution here and you can do this integral, both are these. You expect that the singularities at the endpoints will be rather mild, and the reason is that what happens near t equal to z, you have essentially 1 over t minus z square root, in the denominator there is a square root, and when you integrate it becomes a square root on top. So we expect it to be a very mild singularity, nothing that diverges, but there is a singularity of some kind. In this case they will turn out to be square root singularity on top, z equal to plus minus 1 will have square root singularities, and there will be a logarithmic branch point at z equal to 0. So I urge you to check this out. And now finally, maybe I should stop here for a few minutes. Well, let me finish this and then we could. You could look at what happens to this representation. QL of z I mentioned was half minus 1 to 1 dt PL of t over z minus t. Okay. That was the representation we wrote, L 0, 1, 2. What can we say about the singularities of this function as a function of z? Okay. Now PL of t is a polynomial, so it has no singularities in the finite part of the t plane, but the integrand has a pole, a simple pole at t equal to z. There is no question of pinching here, there is only one singularity. So the only possibility is an endpoint singularity when this t hits either minus, z hits either -1 or +1, nothing more than that. And you expect log, because the PL is regular at that point and dt over z minus t is essentially a log function. So that now explains why you got this value, why at all you had this value, why we had this relationship which said that QL was equal to half PL times this log 1 plus x over 1 minus x plus a polynomial. Okay. So this tells you why. In fact, you can go further. You can ask, as a function of z, we know there is a branch point at 1, there is a branch point at minus 1 for this, for QL, and we could ask what is the discontinuity between these two. So if I come in z and stay here or here, what is the jump equal to? We can compute this, because we are really asking what is QL of x plus I epsilon minus QL of x minus I epsilon, where minus 1 less than x less than plus 1, and what is this equal to? That is the discontinuity. This is equal to limit epsilon goes to 0 half integral minus 1 to 1 dt PL of t times 1 over z is x, so it is x plus I epsilon minus t minus 1 over x minus I epsilon minus t. We are really asking for a difference of this kind. Okay. But we are familiar with this sort of thing, we are very familiar with it from what we studied about dispersion relations. The pole at t equal to x has been displaced a little bit, because the pole is now at x plus I epsilon and this pole is at x minus I epsilon. And in one case you pick up a plus I pi, in the other case you pick up a minus I pi. So all we have to do is to go back and use this formula 1 over t minus x minus I epsilon in the sense of multiplying by a function of t and integrating across the range which includes x. This is equal to the principal value 1 over t minus x, and the pole is below the contour, right, which is equivalent to integrating on top. Okay. So this is plus I pi delta of t minus x. On the other hand, 1 over t minus x plus I epsilon equal to the principal value t minus x minus I pi delta of t minus x, and then this thing is trivial because the principal value parts cancel out completely and you are left with this is equal to 1 half integral minus 1 to 1 dt PL of t, and then there is an I pi and there is a factor. Oh, we should be careful. I should write this as 1 over t minus x minus I epsilon and write this as 1 over t minus x plus I epsilon and pull out a minus sign. So that minus sign stays and I get a delta of t minus x here, another delta of t minus x here when I subtract, because one of them appears with a minus sign and there was a 2 pi I. So I pi, the 2 cancels, integral minus 1 to 1 dt PL of t delta of t minus x, which is equal to minus I pi PL of x. So the jump is just proportional to PL of x itself, and that is why I mentioned earlier that the discontinuity of q nu of z across between the cut between minus 1 and plus 1 is proportional to p nu of z. And we have used the special case of a non-negative integer L to establish that explicitly. The constant of proportionality is minus I pi explicitly. So there are logarithmic singularities. You could also do this by writing the expression for QL in terms of PL and the log function and so on, but this tells you even without doing the integral that this is what it is explicitly. So this is how we evaluate discontinuities using this, essentially using this formula here.